Hi, my name is Manish Gupta, and in this video, I'm going to talk about this model called as TransformerFAM, which uses feedback attention as working memory to support transformer kind of models for large context lengths. Right? So as we all know, transformer models basically use attention, self-attention, which has quadratic complexity with respect to context length, and therefore there's a limit on how much size of input you can provide to these transformer models. These transformer models, of course, are very large, and they basically therefore can encode long-term memory in that senses in their attention weights or in their overall weights. However, from a short-term perspective, they essentially do not have enough working memory to enable longer context lengths as well. Now, one way to basically enable longer context lengths is using sliding window attention. Sliding window attention also allows you to sort of reduce this quadratic complexity to linear complexity. Let's basically quickly talk about how sliding window attention works. So this is an example of sliding window attention. So you have queries here and the keys there, and every query essentially tries to pay attention to only the past three keys, right? So total three keys. So essentially, this is sliding window attention with a window size of 3. So rather than every query trying to compute similarity with every other key, you basically try to compute similarity with only the previous three keys. Okay. Now that's basically, so therefore, rather than actually the attention computation being n squared, it basically becomes 3n because you're just doing similarity computations between every query and the three previous keys, including the current key, right? Um, this kind of stuff is basically done using a ring buffer. So essentially, you store the keys and values only for a particular window, and then you overwrite them with the new one as you move forward, right? Now, a long former actually came up with something called as block SWA or block sliding window attention, where the idea is that rather than having just one hyperparameter window size, they actually have two hyperparameters, block size and memory segment. So basically they say that, hey, we are not going to keep a ring, we are not going to overwrite entries in ring buffer, but we are going to attend to all the info in the ring buffer. So for example, in this particular case, the ring buffer essentially consists of the current segment and one memory segment. So that's basically that. So therefore, the ring buffer is of size 4. And the idea is that it's not going to ever override. It's basically going to pay attention to all of those. So therefore, as you see here, each query actually pays attention to 3 or 4 keys, depending on where its position in the block is. Right, so here the blocks are of size 2, and memory segment essentially says that, hey, it's going to use a memory of 1, which basically means it cares about one previous block. Okay. This one is the same, it is an example of BWSA, but with two segments. So basically saying, hey, I have memory segment size 2 blocks. The block size remains the same. Block size is still essentially of 2 keys or two keys in that senses. And since the memory segment is 2, it basically is going to pay attention to the current block and two previous blocks in that sense. Okay. So that's that. Now, of course, increasing the context length essentially increases the complexity slightly, increase the computation slightly, but the complexity still remains linear. Now, if you look at the receptive field, a receptive field for block SWA can be pretty large depending on the depth of the model, as well as these hyperparameters, block size and memory segment, right? So for example, in this particular case, as you see, this one essentially attends to either 3 or this one attends to 4, which basically means it's of the case BWSA, 2 segments, block size equal to 2 as well, right? But with the depth equal to 4, as you can see, its receptive length basically has just become 8. Okay, so that's that. So a limited, so a receptive field length basically for SWS for SWA is depth multiplied by window size approximately. Okay, so in this case, the depth is 4, window size is 2, so that's basically, or rather, about, well, it's not exactly window size because, well, this is of the BWSA kind. So it's basically the receptive field is about 8. Okay, so that's that. Now, in these SWA style algorithms, the computation of the transformer happens like this. You essentially take the input. So I is the input, O is the output. So essentially, let's say I is over a sequence of length n. and O is an output which is to be generated using an autoregressive kind of a transformer. Okay. Now let tau be the current block. So if you're using BWSA, you have a current block where the current query lies. So essentially, let tau be the current block, and M be the memory segment hyperparameter. So which basically means if I'm using M as the memory segment size, then I'm using past M blocks plus the current block, right? So that's that. So therefore, I care about the keys and the value caches of the past M blocks, right? Um, and the way it works is that it takes the input and you do pre-layer normalization, you compute QKV. So that's the QKVs for the current block. Okay. You actually take the QKVs of the current block up to time point t, because here you have to generate t+1. So you have not even generated, even in the current block, all of those keys, right? So you'll basically take all the keys of the current block tau up to the time point t, and of course the keys of the previous m blocks, right? Similarly, you take the values of the current block and the values up to the for the last m blocks, right? And then you compute self-attention. So you use these keys and values right there along with the query of the current block, query for the current block, and you compute the self-attention. Of course, you take the input and you add that and so on. So if you remember, self-attention also has residual connections and so on. So essentially you compute AT, which is the output of the self-attention layer. You take the output of the self-attention layer, do pre-length normalization, feed forward, and then add that again residual correction. So you add that so as to get the final output of a layer in a transformer. So this is basically the pseudocode for a BWSA transformer. So the way the block sliding window attention works in transformer. Now, how does TransformerFAM differ? So TransformerFAM stands for feedback attention memory. So remember, we basically said that BWSA is great. It can basically reduce the complexity from quadratic to linear. However, its receptive field is rather limited. It's basically just depth into window size. So for example, the prediction for the token at this point cannot really make use of information at this point at all, because it does not line its receptive field. So therefore, the dependencies, the maximum length of the dependency that can be captured using even BSWA is rather limited. And therefore, you need something else to handle long-range dependencies. Okay. Now, as we discussed earlier, long-term memory is basically present as weights, and given that today's large language models are really large in size, that is not a problem, right? However, the large language models have a big problem in terms of short-term memory, or working memory, as you can call it. And it can be best basically expressed in terms of activations. In fact, these broad class of methods are called as compressive memory methods. And the previous video I recorded was also on a compressive memory way of supporting infinite context length, right? So this approach, TransformerFAM, is also an approach to support infinite context length using compressive memory kind of approach. However, there are differences in the way it does, right? So let's talk about details about how this does. In fact, before I go into the pseudocode, right, these are very simple desired data from such a memory, right? So what you would want to do is to basically process the input block by block. And as you processed one block, or you can call it segment or a block, right, you must summarize it in some ways, summarize the keys and values in some ways so that they can be leveraged later for the next block. And when you're leveraging them from the next block, you must also be able to actually recompute the overall, keys and the values of the to be stored in the compressed memory, or rather, overall thing to be stored in the compressed memory, including this block, right? So 4 things that we desire. We want to use the input context, the current block's input context, and the feedback attention memory, the previous context so far, for self-attention computation, right? So we do want to leverage the past memory. Okay. Second, we must be able to update the feedback attention memory when transitioning between blocks. So when you're done processing this block, you must be able to update this memory. You must be able to compress the current block information by conditioning on the previous feedback attention memory into the new feedback attention memory. So when you overwrite it after the processing is done for the new block, for the current block, you must basically incorporate the information so far as well, right? And the most important point, this feedback attention memory is supposed to be a representative of the global contextual information so far, and therefore it should be comprehensive in that sense, so as to compress contextual info indefinitely into this feedback attention memory. Okay. Now, in their particular case, they use this memory of very small length, just 64 Okay, while the block size is of size 1024. So therefore, if you really think about it, the memory actually is much smaller in size compared to the overall sequence length that it can actually manage. Clearly, feedback attention memory gives you linear complexity in terms of compute and a fixed constant size in terms of memory. Okay, so how does it work? Okay, so I tau is basically the input for the tauth block. So essentially, remember each block is of certain size, right? So this is the current block, which is tau, right? So just like in the BSWA case, you basically have the keys and the values for the previous M blocks, which I'm going to use. I also basically have the memory so far. So essentially the feedback attention memory, will represent it as using F. Okay, so memory so far is F. Okay, and I'm going to output the output O and then the feedback attention memory at the next for the next block F tau. Okay, so of course I must output the thing, the output from the transformer layer, but I must also output the feedback memory to be leveraged for the next few blocks. Okay, so the way this is done is as follows. The first few steps remain similar. So you take the input, you do pre-layer normalization, you basically do QKV computation, you compute the QKVs. But you also do the same thing for the feedback memory. So you take the feedback memory f tau minus 1, you do pre-layer normalization, you compute the QKVs. So those QKVs, QF, KF, and VF are your FAM QKVs, FAM query, FAM keys, and FAM values in that senses. Okay. Now, an obvious thing to do is to therefore, compute the keys and the values for the current block. Remember, for the current block, keys and the values for the current block by having, by concatenating not just the keys for the past M blocks and the keys in the tauth block up to time point t, but also leveraging these keys, these FAM keys, right? Similarly, for the value computation, you actually not just use the past M blocks and the current block to the point so far, but also the FAM values. Okay. And then on top of that, you do self-attention. So what does the self-attention mean? The queries of the current block are attending not just on the keys and the values of the current block, but also on the past M blocks, just like in blockwise sliding window attention. Further, they're also attending on the FAM keys and FAM values, right? So that's how this self-attention is computed. And then you essentially just do the another feed forward layer, and that gives you your overall output. That's your overall output that you output as the output of this layer. Hey, but you also need to update the FAM, right? So basically the F, basically you also need to output this F tau. So how do you do that? Okay. So the way you do that is basically you take the FAM keys so far and you add the FAM keys for the current block. Similarly, you take the FAM values so far and basically you add the current values in the current block to the values thing. And then you compute self-attention. So the way you compute self-attention is basically you take the FAM queries and you compute self-attention with respect to these overall bunch of keys and values. Okay. And then you do the same job. You basically just do a residual connection. You do a feed forward layer on top, and that basically gives you your FAM memory. So if you really look at this is actually a replica of this in some ways appropriately, where the input rather than being IT it's basically it's actually in some ways these combination of keys and combination of values and the FAM queries. That's basically that. So in fact, in some ways, the input rather than being IT, it's basically the FAM memory from the previous few blocks. So FAM memory from the previous block. So tau minus 1. So that's that. That's all how TransformerFAM works. Pretty simple. It sort of basically keeps carrying over this memory block by block, thereby encoding the global contextual information indefinitely. So how does TransformerFAM work, right? So basically, the interesting part is that TransformerFAM does not really lead to any changes in the weights in the checkpoint. And therefore, you can actually reuse some existing checkpoints and then just fine tune them in a FAM way with a small amount of data and see how well it performs on long context tasks. So you could reuse existing 1 billion, 8 billion, 24 billion checkpoints, and they actually reuse the flank palm checkpoints. And then they experimented with several tasks. So one of the most popular tasks that people experiment with in this area is passkey retrieval, where the idea is that you have a very long text. Much of it is random text in this, not really absolutely random, but some filler text. And then you sprinkle it with a few occurrences of a important passphrase, you call it passkey. And then at the end, you basically ask a question about the passphrase. And the model is supposed to understand that, yes, this passphrase was there somewhere in this 1 million context length or whatever is the large context length, 200K context length that they experimented with here, and then come up with the right answer. Okay. So in this particular work, they experimented with several different variants of BSWA, right? So essentially, for example, M0 just says one memory segment, two blocks, three blocks, four blocks. Memory with 12 blocks. That is what they experimented with. And they experimented with FAM. Okay. They also compared with RMT and autocompressors, other models which are known to handle longer context lengths. And what they observed is that as the context length increases, of course, with lower context length, several methods can actually give you 100% accuracy in terms of passkey retrieval. But as the context length increases up to, let's say, 200K, it's just this FAM that is able to give you 100% accuracy. Okay. Similarly, even here, when you compare with other methods like RMT and autocompressors, it's just FAM, which gives you really 100% accuracy in terms of passkey retrieval. They also experimented with several other data sets which have long context lengths. For example, Isabella is basically formal theorems data set with the mean context length of 60,000 and a max context length of 2.8K at 280K. And they also experimented with other question answering data sets, which basically require very large context to be able to come up with the right answer. Narrative question answering in Project Gutenberg, books-based question answering, scientific research papers-based question answering, question answering based on a given story or a document, right? And as you can see, their context lengths are really, really large, right? Lastly, they also experimented with the abstractive summarization with context length of about 13,000, right? And they of course compared with several BSWA models, right, with the 8 blocks, 7 blocks, and so on. And they observed that FAM gives you the best results amongst all of those. In fact, this is with 1 billion parameter FAM model, but if you scale it further to 8 billion or 24 billion FAM models versus BSWA models, you can actually see the difference. So you can actually see that FAM models, typically larger the size, they give you better results, even better compared to the 1 billion parameter model. So basically saying that FAM models, the impact of the long context length that it can handle grows with the model size as well. Okay. Okay, so in summary, in this video, I talked about these three models in some ways: sliding window attention, block, sliding window attention, and then TransformerFAM. FAM is basically feedback attention memory, and it allows your transform models to scale to infinite context length. They experimented with various data sets with long context length for tasks like passkey retrieval, question answering, and summarization, and showed that FAM actually works. FAM is actually effective for long context lengths. That's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.